So did we see any patterns? So most of you got these. You figured out, hey, I remember this, maybe from Algebra 2, or I just see how the numbers are related. He said, you know, we remembered logarithm and exponential inverse, so if I'm looking at the numbers in logarithm, I can think of them in terms of exponential. This 5 right here is the what? Base. It's the base of the logarithm and the base of the exponential expression. This is our exponent, and this is the answer to the exponential. Now, this exponent is the answer to the logarithm. Notice that all of these answers were positive whole numbers. Okay? Notice that our base was smaller than the number inside the logarithm. So when the base is smaller than the number inside the logarithm, we should get a positive number, and we're going to most likely not get a fraction if it can go into it. Sometimes you're going to get fractional values, though. Okay, but if it doesn't go in evenly to it, like if this is not a factor of this, or a 5 is not a factor of 25. Here, all of these have negative answers for the logarithm. Well, they all have fractions. They all have fractions either inside the logarithm or as the base. So think about this. 2 to the 4th is 16, right? But it didn't start out as 2. It started out as 1/2. So to make it 2 to the 4th to be 16, we had to flip the 1/2. That made that a negative exponent. 3 squared, 3 to the 2nd, is 9, but I didn't want 9. I wanted its reciprocal, so I needed a negative exponent. So whenever we see fractions inside the log or in the base, then we're going to expect a negative answer to the logarithm because there's going to be a negative exponent. What about down here? Does anybody notice what's different about these than the ones in the first row? Yep, the base is bigger than the number inside the logarithm. And so when the base is bigger than the number inside the logarithm, we're going to have a fractional exponent. That fractional exponent is actually the root, right? This is 25 to the 1/2, which is the square root of 25. Okay? So if the base is bigger than what's inside the logarithm, then we're expecting a fractional answer to the log, giving us the rational or fractional exponent. All right, we're going to look at what a logarithm is. We're going to look at the function of a logarithm and talk about it a little bit. We have, we're going to not write in terms of f of x yet. Log base b of x equals y. B is the base. And y is related directly to the exponent. If we're looking at this in inverse form, it would be b to the y equals x. Now, logarithmic function, it's going to look like this. F of x, that's our height, equals log base b of x. That's without transformations. This is the parent function. We're going to have transformations happen to this. We'll deal with that when we do the graphing part. For today, we're just looking at understanding logarithms and simplifying them. So there's a couple things we want to talk about, though, with this. Remember when we had the function, we had 2 to the x or 3 to the x, right? We had this, which was an exponential function, right? Shoots up infinitely. What's happening as it comes to the left? It's approaching what? 0. So there's this horizontal asymptote for our exponential function. The parent functions have a horizontal asymptote at y equals 0. Well, we said that horizontal or that exponential and logarithmic functions are inverses. How do we write inverses when we're dealing with other functions? What do we do first? What's the first step? Switch x and y, right? So if I switch the x and y coordinates, this is no longer y equals 0. It's what? X equals 0. And then I switch all these points, right? All the x, y coordinates would change. It would be reflected across the line y equals x, basically, is what's happening. We've switched our x's and y's. So this point is this point, and this point up here is this point up here. But instead of having a horizontal asymptote, our logarithmic functions have a vertical asymptote at x equals 0. So this function has a vertical asymptote at x equals 0, which means something for our domain, right? For our domain for exponential, it was negative infinity to positive infinity. The range was different, though. The range was dependent on that horizontal asymptote and whether it was exponential growth or decay. In this particular case, the range would be from but not including 0 to infinity. Well, now, with my logarithmic functions, the domain and range switch, just like x and y switch. I can't go left forever and right forever for my domain. The farthest left I can go but never reach is this vertical asymptote, x equals 0. I can go right forever. I can go up infinitely. I can go down infinitely. So my range is all real numbers, but my domain is affected by this vertical asymptote. So the domain for any logarithmic function is 0, not including 0 to infinity. In other words, when I'm looking at this logarithmic function, the number that I plug in for x has to be greater than 0. It can be a fraction. That's not a problem. It can be any number that's greater than 0. It can be a square root. That's not a problem. What is a problem is negative numbers. Negative numbers can't go in there. In terms of the parent function, now if it's been transformed, if we've shifted the whole graph left 4, well then we could have some negatives that go into that translated function. But on its own, without any transformations, x has to be greater than or equal to 0. Now, that's different up here, right? Well, you're going, well, wait a minute, we had negatives. That's not inside the logarithm. That's the answer to the logarithm. That's actually the exponent. So it's okay for the answer to be negative or for the answer to be a fraction. What I can't have is a negative inside the logarithm. So we're going to look at evaluating some of these. It's going to be similar to what you did in Algebra 2 and similar to what we have above. And then we're going to look at some general rules that can help us simplify more complicated ones. So this is, we're saying 3 to what power is 81, if we're thinking about it in terms of exponential form. Anybody know? 4, 3 to the 4th power, because 3 squared is 9, and 9 times 9 is 81. This one is 5 to what power is the square root of 5? And you're going, well, that's kind of crazy. I have a square root. But what is that square root? What could I write that as a rational exponent? 5 to the 1/2. So the exponent that I need is 1/2. Log base 2 of 2. Anybody know the answer? 1. 2 to the 1st power is 2. So you can think about these in terms of their inverse function to help you figure out what it is going to be. Now I see that I have a fraction in here. What am I expecting my answer to be? Negative. So this is 7 to some power equals 1 over 49. I'm not going to think about the fraction because I know that since there's a fraction, it's going to be negative. And then I think 7 to what power is 49? Well, 7 squared. Make it negative. That will cause you to flip it. So negative 2. 8 to what power is 512? Well, it's not squared because 8 squared is what? 64. What do you think it might be? Let's try 8 times 8 times 8, which is 512, so it's 8 cubed. So the answer to letter E is 3. try letters F and G. Take a moment to try letters F and G, and then we're going to talk about H and I. Anyone have an answer for letter F? Raise your hand if you have an answer for letter F. I would hope at least 4.2 of you, no, I'm just kidding. I'd hope at least 3 of you would have the right answer. 3, right? 4.2 to what power is 4.2? Well, this is 4.2 to the third, so it has to be 3. We'll talk a little bit more about how this looks and how we don't have to think about this as much in a little bit. The next one, I hope that one of you gets it. It's not 1. Yeah, stop. You got to be a little bit negative here. It's -1 because we have a fraction there. So to take 32 to the first is 32, but I have to do the reciprocal, so I need a negative exponent. Okay, this next one's a little challenging, and so when you get stuck, you need to kind of break down the base and see if you can express it as a prime number, or as, at least in terms of this. So right now I have 16 to what power is square root of 2, or 2 to the 1/2? Well, some of you might know, but I actually wouldn't have known just looking at this. So I rewrote this as 2 to the 4th raised to what power is going to give me 2 to the 1/2. Well, if I raise that to a whole number, I'm never going to get 1/2. So what do I have to raise it to? 1/8. I've got to raise it to a fraction so that I get a fraction equal to 1/2. This is 4/8 when I distribute the exponent. 2 to the 4/8 is 2 to the 1/2. So the exponent I need is 1/8. That problem can be a little tricky, so you need to be careful with those. So I've got this exponent. I need to get a fractional exponent, so I'm going to need a divisor. 4 is going to have to be divided by something. So it's 1/8 multiplied by 1/8, divided by 8 multiplied by 1/8. Same thing here. We have 16 to what power is 2. This isn't the square root now, though. It's the cubed root, which is the 1/3 power. And this base is this number is bigger. So I'm going to break that down. This is really 2 to the 4th. I have to raise that to some power. That'll make it become 1/3. Well, if I just raise it to the 1/3, I have 4/3, right? If I made it 4/12, 4/12 equals 1/3. So you could say 4 over x equals 1 over 3 to help you figure out what this would have to be. And it would be x equals 12. So 1/12 is the exponent we need. Any questions on H or I? Those are just a little twist to the whole fractional answer. Basic properties of logarithms we need to try to fit on this front page. We basically have some that are very self-explanatory, and then 2 others that are going to be the inverse properties, which might not be as concrete in terms of your understanding for it. Log base b of 1 will always be what number? Think about it in terms of exponential form. 0, because b to the power of 0 is always 1. Any base raised to the 0 power is 1. So this, if you see a 1 inside the logarithm, then the answer to that is 0, to that logarithmic expression. Similarly, we have log base b of b. Well, you got a logarithm with base b, and inside you have the base. B to what power is b? 1. So if I have this, okay, then it's just going to be 1. Well, that might help the inverse properties. We're going to look right here at the inverse properties. That might help the first one make a little bit of sense. The second one's not going to make a ton of sense to you yet. I've got log base b of b to the x. What's log base b of b? 1. And this even could be like, well, log b to what power is b to the x? The answer is x. X would have to be the exponent. But how we're going to think about this is, if you look at this, I have an exponential function with base b inside a logarithm with base b. So they undo each other, and I'm left with x, as long as they have the same base. Similarly, I could have an exponential function of base b, and in the exponent have log base b of x. It's kind of like square and square root. As long as they have the same base and no other operations, these are going to undo each other, and we're just going to get x. That one is not going to be as intuitive to you until we do some other things with properties, and then you'll be like, oh, that finally makes sense. But right now it may not. All right, so let's take a look at the other side. And some of these problems are just like before, but we actually want to think about them in terms of those properties right now, applying the properties of logarithms. I'm going to rewrite this in terms of a base of 5. Log base 5 of 5, what is 125 anyhow? 5 to the third, 5 cubed. What's log base 5 of 5? It's 1, right? But look at it this way too. I have exponential function with base 5 and a logarithm with base 5. The answer is 3. Another way to look at that, some of you would say, well, of course 5 to the third is 5 to the third. Letter B, I have 12. That's my base, and this is the exponent. But in it is a log base 12. So the exponential base 12 and the log base 12 undo each other. My answer is 4.7. Log base 9 of 9 squared. Exponential base 9, logarithm base 9, they undo each other. Another way to think about that is 9 to what power is 9 squared? The answer would be a power of 2. Any questions on those? Our common log has a hidden base of 10. So it's kind of like the 1 that's always hidden in multiplication, or the square root. We don't put the 2 there. We know that we're doing the square root. And then if we see another number, then we know it's the number of roots that appear right by the radical. So this is, if you see log, oh shoot, I want to make sure I write this right. Log of x, that's really log base 10 of x. And then basic properties of this are the same as the other properties. Log of 1 is going to be what? It's really 10 to a power is 1, so the answer is 0. Log of 10, these are a little tricky because you're not seeing the base there, so you're not thinking about it in exponential form. 10 to what power is 10? 10 to the first. It's the same thing. It doesn't matter what the base is. If it's a 1 inside there, the answer is 0. Doesn't matter what the base is. If it's a, well, it does matter what the base is. If the base is the number that's inside there, then it's 1. For inverses of these, inverse properties, we'd have the following. Log of 10 to the x. Well, this is exponential base 10, and this is logarithm base 10. They undo each other. We're left with x. 10 to the power of log of x. This is an exponential with base 10. In its exponent is a logarithm with base 10. Those are inverse operations like squaring and square root. They undo each other. We just get x. Now, some of the problems that we're going to do are going to work out because we can write them as fractions to solve them. Some of them we may need our calculator for. What's the base on all of the problems that you see for A through F? 10. So as long as we can do 10 to a power to get that fraction, which they might start out as a decimal, then we're okay, or as long as we can use the inverse property. If the number isn't a base, doesn't have a base of 10, that's a factor of it, then it's not going to work out. We're going to need the calculator. So looking at this, do you see anything that you think we might need the calculator for? Which ones do you think we might need the calculator for? A, we actually could rewrite as a fraction. So we will be able to do that, because that's really what? What number is this? 1 out of what? 1,000. So because I can rewrite it as a fraction, I'll be able to do it. And because 1,000 does have a base of 10, if I were doing prime factorization. But what do I expect my answer to be since I see a fraction inside the logarithm? Negative. So I'm thinking 10 to what power is 1,000? 10 to the third. But to make it the reciprocal value, 1/1,000th, I'd need to make it negative. The next one, there's exponential. That's a log base 10. So those undo each other. The answer is 5. Letter C. Is 26 a base of 10? Is 10 even a factor of 26? No. So I'm not going to be able to do that one at all without a calculator. I'm just going to have to do log of 26 and get a decimal approximation. The decimal approximation for that is 1.41. Letter D, anyone have an answer for letter D? 4. 10 to the fourth power is 10,000. There are 4 zeros in that. Here, this one I did try to break down. I said, well, that's really 81 out of 1,000. I can do log base 10 of 1/1,000th, but of 81, I really can't do because it doesn't have a base of 10. It has a base of 9. So this isn't going to help me at all. I'm still going to need my calculator because that has a base of 9. So I'm going to do log of 0.081. And I get an approximate answer of negative 1.09. So that one we have to have a calculator for. What about letter F? Any ideas on letter F? I can't do it without a calculator, right? Because it's not a base of 10, 5 isn't. But there's more to it than that. I can't do it at all. It's a negative. And in our domain for logarithms, the number that goes in the logarithm has to be greater than 0. If that's x, x has to be greater than 0 is our domain for any parent function that's a logarithm, unless there's been a transformation. Now, if this was x minus 5 or x plus 5, then I could put a negative in there, but we're not there yet. We'll get to it in transformations. So one that you probably did not do in Algebra 1, most of you, would be, or some of you even in Algebra 2, is the natural logarithm. A natural logarithm has a base or a hidden base of e. So natural log of x is really log base e of x. You're like, e? What the heck is e? E is an irrational number, much like pi, that is a natural base. In some real-world problems, that's how we found it, E ends up being the base for some natural population models, for some other models as well. So we'll get into some of that later. The basic properties for natural logarithms are the same as the properties for any function. The natural log of 1 is 0. The natural log of e, remember that has a base of e, so what's that? 1. And then its inverse properties. The natural log of e to the x. This has a base of e, and it's in log, and this has a base of e. It's an exponential inside the log, so they undo each other. We get x. E to the natural log of x. This has a base of e for the exponential expression. The logarithm is in the exponent with a base of e, so they undo each other. The answer is x. So using that, see if you can evaluate letters A through F. Some of them might trick you, and there's some that aren't going to have a base of E, so you might have to use the calculator. But see if you can figure out some of them that you can get pretty quickly for A through E. Anyone have an answer for A? What is it? 0.73. A, that's correct, 0.73. They're inverses, this exponential and this logarithm, so they undo each other. What about letter B? Not going to work. Not possible. Oh, by the way, I should have said that for F too. There's no solution for that one because you can't do log of a negative number, can't do the natural log of a negative number. I see a fraction in letter C, so I'm expecting my answer to be negative, and in fact it's negative 3, because this is e. E to what power is 1 over e to the third? Well, it would be 3 to make it e to the third, and negative to make it flip. Does 32 have a factor of e in it? No. E is irrational, so it's not going to go into 32. And so the only way to evaluate that is in the calculator. On the calculator, between the 4 and the 7 keys is an ln key for natural log. So you click natural log of 32 to get a decimal approximation, and that is 3.47. Was there a question over here? Okay, okay. Letter E, what operations between the 2 and that natural log? Multiplication. So I have 2 times whatever comes out of this. Well, this is exponential with base E. That's logarithm base E. They undo each other, leaving me with 14. 2 times 14 is 28. And last but not least, the answer for F, I would hope that at least 6 of you would get this correct. 6. Hopefully all of you got it correct. All right, we're going to look at one final concept today. We will expand on this as we make them more complicated and have to solve them more involved. But finding inverse functions, finding the inverse of an equation, we have y equals 5 to the x. So this is exponential, right? How do we undo an exponential? What is its inverse? What's the inverse of an exponential function? A logarithm of the same base. We're going to undo exponential functions using a log of the same base. Now, and before you do this, you have to get that exponential expression by itself. So I don't have anything added or subtracted outside of it, nothing multiplied with it. So I have just that. And also, the first step to finding an inverse is to do what? Does anyone remember from earlier? Switch x and y, yes. So we start by writing x equals 5 to the power of y. And now we've got to undo, we've got to get to this exponent y. To do that, we're supposed to use a log of the same base. Right now, the base is 5. So on the left-hand side of this equation, I'm going to do log base 5. And on the right-hand side of the equation, I'm going to do log base 5, because whatever I do to the left, I've got to do to the right, or else the equation won't be balanced. Into this, I'm going to plug in, on the left side, the x, and on this side, the 5 to the y. So I had this equation, I just did the log base 5 of both sides. Well, this side stays log base 5 of x. What happens over here? Yeah, we're using that inverse property, log base 5, exponential base 5. Those are inverse operations. I'm left with y equals log base 5 of x. Some of you, I've had students before who thought, oh, I'm just going to make it a logarithm with base 5. That works for this problem. It won't work for the next two, so it's better to go through these steps. For For letter B, the first thing to do is to get the log by itself. It is because the 2x is inside of the logarithm. So now I'm going to switch x and y. X equals log, what's the base on this log? 10 of 2y. We're trying to solve for y, so we got to get to that y variable by undoing the logarithm with a base 10. How do I undo a log with base 10? What do I have to use? What's the inverse of a logarithm? Sorry. Exponential with base 10, yes. Yes, it's just like the inverse of squaring is the square root. It's just a little different because they're actually written out as logs. So we're going to do exponential base 10 on both sides. I've got 10 to a power and 10 to a power on both sides. And what's going to go in that exponent is the stuff that's in the equation. So I'm taking my equation, and these were equal, right? I don't know what they are, but if this is 2, let's say that x is 2, then this thing works out to be 2 also. So then if I plug it in here, 10 squared and 10 squared should be the same. So I'm just putting my x here and my log of 2y here. Well, what happens on the right-hand side? They cancel. I got log base 10 in the exponent of an exponential base 10, leaving me with 2y equals 10 to the x. Now here's where students mess up. They get all this, they're like, I can undo logarithms, I can do exponents, that's awesome. And then they screw this up. Here's what they do. I have students who tell me that they can write y equals 5 to the x. You cannot write y equals 5 to the x. If that were 10x over 2, because it's multiplication, I could reduce the 10 halves. But this 10 is being raised to a power. We don't even know what the power is yet. And then it's being divided by 2. So order of operations says I can't divide the 10 by 2 until I've done the exponent. So this is as far as this equation can go. Letter C, what should I do first? Switch x and y. What do you think I should do next? Any suggestions? Taylor, any suggestions? No? Well, is this whole thing the exponential expression or just part of it? Just part of it. So it's not by itself yet, right? So what am I going to do to get it by itself? Divide by 2. So I now have x over 2 equals 3 to the y. Now that the exponential expression is by itself, I can undo it. But notice its base is 3, so what am I going to have to use to undo exponential base 3? Somebody said it. Log base 3. So I've got log base 3 on the left and log base 3 on the right. Whatever I do to the left, I got to do to the right. So I'm basically taking my equation and I'm taking the log of both sides. So those are going right inside those logarithms. So this is what I have on the left-hand side. On the right-hand side, log base 3 of 3 to the y, the exponential and logarithm undo each other. That's why we chose that. So y equals log base 3 of x over 2. There's our function. Your practice tonight comes from page 178. Most of them are going to be real simple. There will be a couple you'll have to use the calculator for. The other ones you want to try to do without the calculator. You're doing 1 through 27. Okay. Tomorrow we will look at graphing logarithmic functions and their transformations and figuring out the domain and range and end behavior, all of that stuff. On Thursday and Friday we're going to cover properties of logs. We'll review how to condense and expand them. And then you'll have some days to review next week, Monday and Tuesday, and a quiz on Wednesday.